Welcome to this video lecture series on transportation engineering. In this session, we shall discuss on the highway drainage. So what actually is highway drainage? Highway drainage is the process of removing and controlling the excess surface and subsoil water within the right of way. During the rains, the part of the rainwater which flows on the surface and part of it percolates through the soil mass as the gravitational water under its until it reaches the groundwater table. The removal and diversion of the surface water from the roadway and adjoining land is termed as the surface drainage. And the diversion or removal of the excess soil water from the subgrade is termed as subsurface drainage. Some water remains in the pores of the soil mass by the surface tension and adsorptive forces which cannot be drained off by the normal gravitational methods, and this water is termed as the held water. The significance of the drainage. The excess moisture in the soil subgrade, it causes the considerable lowering of its stability, and the increase in the moisture, it causes the reduction in the strength of many pavement materials like stabilized soil and waterborne macadam. Next, in some clay soils, variation in the moisture content causes the considerable variation in the volume of the subgrade, and this sometimes contributes to the pavement failure also. The formation of the waves and corrugations in the flexible pavement is due to the poor drainage. It causes failure due to the stripping of the bitumen from the aggregates. The mud pumping is due to the presence of the water in the fine subgrade soil. Excessive water on the shoulders and pavement edges causes considerable damage to the pavements. The excess moisture, it causes the increase in the weight, and thus it increases in the stress and reduction in the strength of the pavement, and this is one of the main reasons of the failure of the earthen slopes and the embankments. The freezing temperature are prevalent in water, and the presence of the water in the subgrade and continuous supply of water from the groundwater can cause considerable damage due to the frost action. And lastly, the erosion of the soil from the tops of the unsurfaced roads and the slopes of the embankment cut and hillside is also due to the surface water. Now we'll discuss regarding the requirements of the highway drainage. The surface water from the carriageway and the shoulder, it should be effectively be drained off without allowing it to percolate onto the subgrade. The surface water from the adjoining land should be prevented from entering the roadway. Next, these side drains should have sufficient capacity and longitudinal slope so that the water it may be discharged with ease. And the flow of the surface water should not cause formation of the cross ruts or erosion. Next, the seepage and other source of underground water should be drained off. The highest level of water table should be kept well below, as if there is a rise in the water table, it may lead to the rise in the water table by the capillary action in the pavement layers, thus leading to the water logging and causing the pavement layers to settle. In the waterlogged areas, special precautions it should be taken. Next, we shall discuss on the surface drainage. The water is first collected in the longitudinal drains, generally in the side drains, and then the water is disposed of at the nearest stream, valley, or the water course. The cross drainage structures like the culverts and the small bridges may be necessary for the disposal of the surface water. The methods of the surface drainage: first is the longitudinal side drains method. Second is the catch basin and inlets in the urban areas. Next, providing dam proof courses. Next is the providing the proper camber to the pavement roads. Next is providing sufficient slopes to the sides. And lastly, keeping the level of the carriageway at least 60 cm above the high flood level. So the first case, where the side drains for the roads in embankment are to be provided. So it is necessary to provide a side drain on one side or both the sides when the road is constructed in the embankment. The side drains should be at least 2 meters away from the bottom edge of an embankment, so that the lateral entry of the water through the side drain should be avoided into the embankment road, and the depth of the side drain is kept as 1 to 1.5 meters to prevent the entry of the side drain water into the embankment as well. As you can see from the figure, we have a road in the embankment and the provision of the side pit at a distance of 2 meters and at a depth of 1 to 1.5 meters from the road pavement. Next is the side drain for the road in cutting. As you can observe from the figure, we have a road which is being constructed in cutting. That means a mountainous terrain or a sloping terrain is being cut, and then into this cut portion the road is being constructed. Here the provision of the side drain is necessary in order to collect the water from the sloping terrain, so that it will avoid the entry of the water onto the pavement surface. And sufficient slope should be provided to the side drain so that the water from this sloping drain, which may be in excess, can be effectively drained off. Next is the catch basins and inlets in the urban areas. The catch basin, as we can see from the figure, is a chamber-like structure which is constructed on a sewer line. The water from the pavement surface is collected in the catch basin and discharged to the sewer line. As you can see from the figure, from the top surface, the water from the pavement surface gets drained into the catch basin, and all the debris it settles to the bottom, whereas the clear water it is discharged to the connected sewer, which actually avoids the entry of the debris into the municipal sewer lines, thus avoiding any sort of blockage in the rainy season especially. Next is the shoulder drainage. Now, for the quick drainage of the water from the roadway, the shoulder has to be properly sloped. This proper slope should be provided. So the first case, the continuous drainage layer of 75 to 100 mm thick should be laid under the shoulder at the bottom level of the subsurface or the bottommost granular subsurface layer extended up to the edge. And this paved shoulder, it should be provided with a slope of at least 0.5% more than that of the camber and to the paved shoulder. And for the unpaved shoulder, this slope it should be again exceeded by more than 0.5% with respect to the paved shoulder, so as to drain off the water from the pavement surface effectively. The median drainage. Now, except for the median less than 5 meter wide, it is not desirable to drain the median area towards the pavement surface. In general, a 1.2 to 1.8 wide median provided with the curves and which is always paved. 1.8 to 5 meter wide median, usually turfed and crowned, so that the surface water could run towards the pavement, maybe with or without the curves. Third case, the median wider than 5 meter are without any curves at the edge, and if the carriageway slopes towards the median, then the central drain may be made to carry the runoff, and the slope should not be steeper than 6:1. And when the median has only earthen surface, it should not be crowned because it can result in the soil particles to be carried to the pavement surface, making it more slippery. Now the subsurface drainage. Subsurface drainage is an attempt to keep the variation of the moisture in the subgrade soil to a minimum level. And the change in the moisture of the subgrade are caused by the following methods. First is the fluctuation in the groundwater table. Second, the seepage flow. Third, the percolation of the rainwater. Fourth, the movement of the capillary water. And next is in the subsurface drainage, it is practiced to keep the variation of the moisture in the subgrade to be minimum. So what actually or where actually we should provide the subsurface drainage? Subsurface drainage becomes essential when the road is in cutting and the water is seeping from the sides. Second, when the road is near to a foothill or hill, and it is likely to be damaged by the water flowing down the hill, as this water not only flows onto the surface, but it also may regain velocity due to the gravity by which the water flows from the top of the hill to the bottom, and this can cause the erosion of the road surface. Third, when the road is passing through a plain area and the water is likely to accumulate on its sides. As this water, it may percolate into the layers of the pavement, thus leading to its disability. Next, when the water rises up to the subgrade by the capillary action. If the water rises up to the subgrade by the capillary action, it may weaken the subgrade of the pavement, thus leading to the settlement of the base course and the surface course eventually. And lastly, where the subgrade soil is affected by the drain passing near the road. Next is the lowering of the groundwater table in the pervious soil. If in case the soil is relatively pervious, the longitudinal drain trenches with the drain pipes backfilled with the filter sand can be used. As you can see from the figure, for the carriageway or the pavement, with the provision of the shoulder, at the end of the shoulder we have provided the longitudinal trench, and at the same time there is a provision of the longitudinal drain pipe with the sand filter. Here the water at the depth of the trench depends on the extent of the lowering required, the soil type and the distance between the trenches. If the water it gets percolated from this site, as the soil is pervious, in that case the water, if it tries to come in contact with the subgrade and the base course of the pavement, in that case the sand filter it allows the water to percolate to the longitudinal drain pipes, which can effectively drain off the water, just avoiding the lateral water to come in contact with the pavement layers. Next, lowering of the groundwater table in the impervious soil. So if the soil is relatively less permeable, the lowering of the groundwater table may not be adequate. Hence, in addition to the longitudinal drains, transverse drains have to be installed at a suitable interval. As you can see from the figure, a typical sketch of the subsurface drainage system with the longitudinal traverse drains can be seen. Next is the control of the seepage flow. When the general ground as well as the impervious strata below are sloping, the seepage flow is likely to exist. If the seepage zone is at the depth less than 0.6 to 0.9 meters from the subgrade level, the longitudinal pipe drain in the trench filled with the filter material and the clay seal may be constructed to intercept the seepage flow as shown in the figure. The seepage line can be lowered to the desired depth. As you can see from the figure, we have a sloping ground and there is a provision of the filter material and a perforated pipe at its bottom, and we can see the lowering of the zone of the seepage flow, that is the seepage flow line, to the perforated pipe as compared to the original seepage flow if there is no provision of the filter media and the perforated drain pipe. So in this case, if there is no provision of the filter material and the perforated pipe, the seepage line would come in direct contact with the pavement material, thus leading to cause instability to the pavement materials. So in this case, the addition of the filter material and the drain pipes, it leads to the lowering down of the seepage line, thus maintaining the stability to the subgrade to the pavement surfaces. Next, the control of the capillary rise. If the water reaching the subgrade due to the capillary rise is likely to be determined, it is possible to solve the problem by arresting the capillary rise of the water. Granular material of the suitable thickness is provided during the construction of the embankment between the subgrade and the highest level of the subsurface. The thickness should be sufficiently higher than the anticipated capillary rise within the granular layer so that the capillary water may not rise above the cutoff layer. The capillary cutoff may even be in the impermeable bituminous layers, and the location of the cutoff should be above the level of the capillary rise expected for the clayey subgrades. From this figure, we can see the capillary cutoff for a clayey subgrade, wherein there is the provision of a pervious layer above the clayey subgrade. With this, we shall stop. Thank you.